class. Welcome to the 0th mini lesson in PY203. I just want to spend a little bit of time talking about what the class actually is and what the term modern physics actually means, and talk about a little bit of special physics that is not in the textbook directly, but is relevant to modern physics considerations and pretty interesting to think about if you're into physics, which I hope a lot of you are. So it's important that modern physics doesn't actually mean physics that's actually all that new. It's not the same as contemporary physics. So modern physics is talking about ideas in physics that extend essentially from about 1900 to about the middle of the 20th century and around 1950. Right? So this is the time when the theory of relativity in both its special and general form were developed, when we realized that we needed to invent quantum mechanics to describe atomic, subatomic, molecular motions, when we realized that the existence of the atomic nucleus requires new physical laws, etc. And so modern physics is a very specific time frame in the history of physics that extends for about this 50-year period. I guess I'd break the rest of the recent history up sort of from about the 1950s. You have sort of old topics that are still not really contemporary, and then maybe about the last 10 or 20 years you can think of as contemporary, and so that's a sliding scale, right? You keep moving this yellow block up as time goes on. So yeah, I think Professor Daniels, who some of you may know in our physics department at NC State, makes the point that modern physics is modern in the same sense that modern art is modern, right? The modern art extends, back into include artists who have been dead for a very long time. I don't remember the exact definition, to be honest, but it's definitely not only recent art, but contemporary art is, right? So people who are essentially, the word contemporary means happening today, practicing today, but modern is this very special blue period, and that's what we're going to talk about for this whole course. For this course, we may occasionally bring in some contemporary topics that are sort of natural evolutions of the modern physics era, just for fun. But for the most part, we're going to be sticking in this blue and a little bit in the green area. Okay. So the most important part about this course is really up to the first midterm, in my opinion. I mean, that's really, in my view, that's really why you're here, and that is the thing that you need to retain from this course. So we want you to become functional users of special relativity and basic quantum mechanics. That's going to be the topic of the first midterm, and we'll start doing actual lecture content about that in the next mini lesson 1. So after the second midterm, what we're going to basically do is start to give you a survey of all the subfields of physics. So we'll be talking about atomic physics. That's quite important, and so there's a little bit where I would say you should be retaining a significant part of the atomic physics in this, and in some ways, right, that's sort of another example of quantum mechanics. But then as we go deeper into the applications in molecular physics, nuclear particle cosmology, we would expect you to retain less after you leave the course, because there's so much, right? I mean, that's the hard part about this course is the survey part of it is a lot of different material, and it's definitely hard to retain it all, easy to become overwhelmed. It's not you, it's the course. That's just the way it is. We want you to have some experience and some contact with a lot of the topics in modern physics. So, yeah, I'm saying you will probably feel overwhelmed, and that's, I guess I'll claim it's a feature, not a bug, right? To have to take a survey of all of modern physics is a big challenge, and Again, you're not supposed to become nuclear physicists or cosmologists by taking this course, but you're supposed to start to get a feel for it, right? And so I have the same problem, right? Like, I'm not actually a nuclear physicist, and so suddenly I have to spend whatever, a week or 10 days teaching nuclear physics. It's actually scary. I'm always worried I'm going to mess it up. So, but one thing about this is if there's a topic that you really want to know something about, you can kind of push me and kind of say, well, what if we talked about this? Or how does a nuclear reactor work? Or what about chaos theory? Like, technically, I don't purposefully teach chaos theory. I kind of try to bring a little bit into our study of statistical physics in this second half of the course. But for example, if you're really into like chaos theory and nonlinear dynamics, you might sort of push on me and say, I'd like to hear more about that. And I can probably adapt this survey part of the course to be more responsive to what people are interested in. So let me just show you where this course sits within the physics major degree program at NC State. I know probably not all of you are physics majors. I can't quite remember what everybody is doing, but quite a lot of you are physics majors. And so it's worth thinking about the place that this course has, which is a little bit weird, right? In the same way that you've got this weird survey in the second half of the course, you've sort of got a weird position of the course within the physics degree program. So you start out with your mechanics and your E&M courses, which are, pretty standard and sort of a natural evolution, I would guess, of physics courses that you might have had in the past in high school or elsewhere. So what's going to happen in doing an actual physics degree is you make this huge jump in sort of performance expectations in the course when you get to the 400 level courses, and that'll be next semester, so spring of 2021 for most of you who are majoring in physics. And so PY203 sits right at the cusp of this huge jump, right? And so it's not clear where it ought to sit within this jump. Does it get pushed up sort of to the halfway to the the inflection point? Should it? Or should it be far down here and more like exactly PY202 level expectations? And so where it sits actually sort of depends, in part on the instructor, in part on, and in part on what part of the course we're in. So I'll make a claim that the survey part of the course is way down here in the PY201, 202 level, where you're really doing simple algebra using simple formulas. The first half of the course, where we're doing special relativity and quantum mechanics, is further up the slope here, right? Where we're really expecting you to do sophisticated physics, retain it, and have a deeper non-survey level understanding. And so there's a little bit of weirdness in this. So I made up this plot on the whiteboard. I guess it was last fall when I taught PY203, and I made it up sort of in discussion with other physics faculty, and so I think we mostly agree about this, that there's a huge jump between the 200 level and the 400 level courses, so that these PY411 and 413, so this is thermal physics, which I often teach, and mechanics, this is often a big shock to students. And then you have a kind of gradual thing for a couple semesters until you get quantum mechanics. And quantum mechanics is also another type of shock. So I think this plot is accurate. Yeah, so let me know if you have any questions about sort of degree program. I actually am a physics advisor. I'm not sure if I'm any of your advisors. I kind of lose track of everyone. I get assigned new advisees. So you maybe that you've been assigned to me this semester and I don't know it yet. So hello if you are. All right, let's talk about a little science though, because this is sort of just academics. So the basic idea about the modern physics era is that we have these two big changes to how we describe nature. So in quantum mechanics, we need to invent new kinematics and dynamics for how we talk about the motion of very small scale constituents of matter. So atoms, electrons, nuclei, even molecules. We realize that we need to be able to treat them consistently either as particles or as waves depending on the situation, right? And so that's an unusual new realization that happened in the modern physics era. And then in special relativity, we realized that essentially because of discoveries in electromagnetic wave propagation, that we have to modify our theory of space-time, which is the setting for physics. And always in special relativity, we are ignoring the effects of gravity. And so these were really big changes. And in this next set of slides, what I want to do is just remark on the things that did not change in the modern physics revolution. And so I would say the most significant thing that did not change is conservation laws. We really tried to maintain almost perfectly intact all the conservation laws that we thought we knew going into the modern physics era. The only one that will be destroyed utterly is conservation of mass. And so we'll talk about that in a couple weeks. But the conservation of energy, conservation of momentum, conservation of charge, conservation of angular momentum, all these things were maintained and really almost by necessity, right? Because people have so long realized how valuable and useful conservation laws are that the motivation to keep them intact is really, really strong. So let's talk a little bit about conservation laws in the context of what's called Noether's theorem. And so this is a rigorous connection between conservation laws and symmetry. And when I say rigorous, I mean it's mathematical. It's very important to recognize that there's a difference between math and physics. Physics, is not necessarily, I guess it's not necessarily constrained by the rules of logic the way math is, in the sense that in physics, you take as your premises, your postulates, if you want, experimental data, right? And you sort of regard that as absolutely true. And then you build your theories around those premises based on experimental data. In math, I guess the premises are sort of basic logic rules, right? And you sort of build everything around basic logic. So when I say rigorous, I mean mathematical as opposed to physical. So based on logic rather than experimental observations. And so there's a theorem that says that for every continuous symmetry, there is a conserved quantity. It doesn't necessarily tell you what the quantity is. There are ways to figure out what it is, but it does says that it exists. And so you'll actually be able to prove this in your mechanics, your 400 level mechanics class if you're a physics major, so PY203 or 412, using Lagrangian mechanics. I'm not 100% sure which of these it falls in. I guess it probably also depends on the semester. And so this theorem was first proved in generality by Noether, who was a very famous mathematician, again, sort of working in the modern physics era in the early 1900s. And her theorem completely survived the quantum revolution. And in fact, it appears as essential in more advanced quantum field theory, which is the basis of the standard model of particle physics. And so she's a very interesting person to pay attention to, sort of her life and her struggles. She was, by everybody's judgment, a really significant genius, but for a very long time she was not paid. And so in particular, when she proved this theorem, she was not being paid for the work that she did because she was a woman. And so here's a quote from Einstein in 1935, and by this time everybody had sort of realized Noether's genius. And he says, "Judgment of most, living mathematicians, Fraulein Noether was the most significant creative mathematical genius thus far produced since the higher education of women began. So it's extremely high praise for sure, but also it actually contains a little bit of bias and shade within the statement, right? Because he sort of feels compelled to not just say she's a significant mathematical genius, but needs to sort of qualify it by talking about the fact that she's a woman and that there haven't been many women. And so, you know, there's an implication there that maybe she's not that much of a genius. So I've occasionally read on the internet that people misquote Einstein with regard to Noether by sort of leaving out the fact that he was compelled to qualify his statements about her. That bias still exists in physics, of course. So let's keep going and talk about this theorem. Again, so you can prove it. And when I say prove it, you prove it mathematically. Can I say one thing about physics compared to math? When we have a law of physics, we almost never prove it, right? It's basically a statement of experimental fact. You don't use math to prove laws of physics, ever. If anybody tells you they are, one of two things is happening. They're not telling the truth, or the law that they're talking about is really a math fact and not actual physics. And in fact, Noether's theorem is a math fact. It's not physics. It has physics implications, but it is a math fact, and that's why it is considered to be rigorous. So important examples of for every continuous symmetry there is a conserved quantity are if you have space translation symmetry, that implies that momentum is conserved. If you have time translation symmetry, that implies energy is conserved. And again, when you're in Lagrangian mechanics, this turns out to be really easy to show. Like, it's sort of surprising how easy it is once you have the tools of this mechanics formalism. We should say specifically what we mean by space translation and time translation symmetry. So what we mean is essentially that if you have space translation symmetry, it means that the laws of physics don't change as you move from place to place in the universe. So the equations that you have deduced from experimental observations apply equally well, say, at coordinate x equals 5 as they do at x equals 27.2, okay? So that seems to be an experimental fact that space translation symmetry exists. I think, you know, it could be overturned, but it seems to be a fact. And time translation symmetry is the same fact for differences in time, right? So the laws of physics that Newton deduced by considering motions of the moon are the same as they are today, even though time has been evolving. All right? So that's what we mean by symmetry in this context. So again, you can prove this simply with some more advanced techniques than we have in PY203, but I always wonder, can we find a way to motivate it, not prove it, but motivate it using ideas that we would know in PY203. I actually found this interesting document from a mathematician named Gabe Kahn, who I think now is a postdoc. I'm not sure where he is, maybe Michigan State, but when he was a graduate student at OSU, he actually gave a talk and wrote a little document called What is Noether's Theorem, where he makes a really interesting point that you can sort of start to talk about Noether's theorem just by looking at things like the work-energy theorem. So let's take a look at how time translation symmetry implies that energy is conserved, motivated by the work-energy theorem, work-kinetic energy theorem. So again, this is not a proof. It's not rigorous in the sense that Noether's theorem is a proof. It's just a sort of plausibility argument for why is there particularly a connection between energy and time, okay? So the work-kinetic energy theorem, if you remember from mechanics, comes from when we define work, the differential element of work as F dot dr, where dr is a differential displacement along the path that the force is acting. And so let's substitute on the left F equals dp dt, that's Newton's second law, and dr equals v dt, so F is equal to p over m dt. And so we substitute in to get the differential work just in this form, where we've been able to cancel the dt's. All right, so d work is p dp over m. And so we can't really deal with this expression in this way. You know, it's true, but it doesn't really help us very much, so we need to rewrite it. And so let's define a quantity k, which is equal to p squared over 2m. You may recognize that as the kinetic energy, but for now it's just something we made up. And so p squared over 2m you can also write as p vector dotted into p vector. And then we can apply the product rule to say that the differential of k is equal to 1 over 2m p dot dp plus p dot dp, so 2 p dot dp, and the 2's cancel. And so dk, the differential change in this quantity that we defined, is just this expression p dot dp. And so we just showed on this slide that the differential work done is equal to the differential in this funny quantity. And let's just call it the kinetic energy, because we know that's what eventually we would call it if we were in a mechanics class. All right? So now let's just go back and integrate the differential of work, right? So the total work along a trajectory is equal to the integral ki to kf of this new quantity, the kinetic energy. And so this is the work kinetic energy theorem. It says that the work done is equal to the change in kinetic energy from the start to the end of the path. Now let's return to our starting definition of work, but write it out as an integral. So change in kinetic energy is equal to the total work, which is the integral from the initial position to the final position of F dot dr. All right? And so the connection to time is really interesting here in the sense that you're doing explicitly this integral. It's a line integral along a trajectory, right? But you know, as I've drawn in this little picture, that there's an implicit time variable along the trajectory, right? It's sort of hidden in the integral. Like, strictly speaking, if you knew the geometry of the trajectory, you wouldn't need to include time at all. I mean, you might end up parametrizing by time for convenience, but you don't necessarily need it, right? You can just sort of do the integral as a line integral. And so the point is, let's imagine we have a scenario where delta k equals 0, where kinetic energy would be conserved, right? To make sure that that's always the case, we can't sort of wait and shift in time to defeat the conservation. You get what I mean, right? So if at one particular time from time interval delta k equals 0, if time translation invariance were not true, you could just wait until later or do the integral earlier and find that it would not be delta k equals 0, right? And so this hidden time variable in here is sort of telling you that you must have time translation invariance in order for this integral to make sense and for conservation to exist independently of when you decide to do the integral, I guess. Again, so this is a hand-waving argument. I'm totally admitting it, but I think the point is, how do you make a connection between energy conservation and time translation symmetry? And so energy is appearing in this theorem, and time translation symmetry is essentially implied by the hidden time variable inside this integral. So another way to say this is, for this to make sense in the context of an energy conservation law, you can't let the force law suddenly change at some time, or even gradually change over some time. So you can do a similar thing to show that there's a connection between space translation symmetry and momentum conservation. So if you write the impulse momentum theorem, which is very similar in appearance to the work kinetic energy theorem, you find that the change in momentum is equal to the integral from an initial time to a final time of the force over the time interval. And so once again, there's a hidden variable here, because as your time is evolving, strictly speaking, you can be changing your position of where you are in the universe, right? And so once again, we make the association that if there were not space translation symmetry, as we defined it before, you could make nonsense out of this integral by just going to a different place in the universe, right? And so this, to me, is a good connection between momentum conservation and space translation. Again, you make it rigorous when you use Lagrangian mechanics. And these are not rigorous proofs. They're not even perfect arguments, right? It's completely hand-waving, but these are, in my view, decent plausibility arguments to motivate the connection between time and energy conservation, space and momentum conservation. And so let me just remark, if you have space rotation symmetry, you would have angular momentum conservation. And so if you like this kind of argument, I'm going to suggest that you would try to come up with the hand-waving plausibility argument for the connection between space rotation symmetry and angular momentum conservation, okay? See if you can do that. It's not you're not going to be tested on whether you can do that, because it's really quite a vague and hand-waving discussion. But I do think it's interesting to think about. All right, so let me just blow your mind for a minute and then we'll stop. If you look at Einstein's theory of gravity, which we're almost not going to talk about at all in this course, it turns out there is no time reversal symmetry, and therefore energy in the universe as we know it seems to not actually be conserved if you care about gravity, right? Now, this is pretty shocking. And so this is Einstein's theory of general relativity. And in this theory, the universe is expanding, and in fact, it's expanding at an accelerating rate. This is the dark energy mystery that we may talk about a little at the end of the course. And so what it means is that time translation symmetry is broken, right? The universe is not the same now as it was 6 billion years ago, okay? And so the way that matter moves, the force laws change with time. And so Noether's theorem says that in this case, we don't have energy conservation. So we're not going to spend much time talking about this, but I would actually strongly recommend that if you like this type of physics, that you watch this episode of the PBS Space-Time, which is a short video you can click on YouTube. It actually talks about this interesting connection and Noether's theorem. Yeah, I think that's all I want to say for this lesson. And in the next lesson, mini lesson 01, we'll actually start doing the really important physics that's part of the actual course content of PY203. So we'll see you then.